Hi everyone, welcome to another session of the HBL files. In today's session, we will be talking about wave energy in terms of intensity, power, and amplitude. Intensity is defined to be the rate of energy transmitted per unit area at right angles to the wave velocity. Let us interpret this definition part by part. First is the rate of energy transmitted. When we talk about rate, it has something to do with time. This phrase actually tells us about energy over time. Now, this energy was transmitted per unit area. So that means this will become energy over time over area. And the area is at right angles to the wave velocity. So this area is the cross-sectional area. This whole expression over here pertains to intensity. Notice that energy over time is equal to power, which is represented by the capital letter P. If we represent intensity using the capital letter I and cross-sectional area by the capital letter A, we then have this formula. Intensity is equal to power over area. We then use this equation to solve this problem. A 100-watt lamp emits electromagnetic radiation in all directions. Assuming the lamp to be a point source, calculate the intensity of the radiation at a distance of 1 meter from the lamp and at a distance of 2 meters from the lamp. Now, notice that in this problem, we were given with two conditions. First is that the lamp is assumed to be a point source and that the electromagnetic radiation is emitted in all directions. That means the problem will look like this. We have the point source. The electromagnetic radiation is emitted in all directions. That means the energy is also being emitted in all directions. So if we look at this formula, this area cannot be a simple area or a piece of area like this. This area should be the whole area surrounding the point source, which is equivalent to the surface area of a sphere. Notice that r here represents the distance from the source. So to solve letter A, we just have to replace r by 1 meter, giving us an intensity of 8 watts per square meter. And then for letter B, replacing r by 2 meters, the new intensity will now become 2.0 watts per square meter. Notice that in letters A and B, the power was kept constant. Since that is the case, we can say that the intensity is inversely proportional to the square of the distance, which means that if we double the distance, we are reducing the intensity to 1/4 of its original value. Next will be the intensity and the amplitude. The intensity and amplitude will generally decrease as the wave propagates. These are the following reasons or possible reasons as to why that is the case. First, as we have seen in the previous example, the waves can spread out from a point source. Second, waves can be absorbed. And third, waves can be reflected or scattered by objects. Now, intensity and amplitude is related through this. Intensity is proportional to the square of the amplitude. In symbols, it will look like this. Turning this into an equation, we have I is equal to Ka squared. And finally, we have the ratio of intensity to the square of the amplitude equals constant. Now again, this K over here is simply a constant. Notice that we are also using capital A to represent amplitude. So make sure that when you are solving for intensity, you know what the capital letter A means, whether it's area or amplitude. Let's use that formula to solve this problem. Waves from a source have an amplitude of 5 centimeters and an intensity of 400 watts per square meter. The amplitude of the waves is increased to 10 centimeters. What is their intensity now? And the second question, the intensity of the waves is decreased to 100 watts per square meter. What is their amplitude? Now, again, we'll make use of this equation. And since we are given with two conditions, we can rewrite this into this equation. So the ratio of the first intensity over the square of the initial amplitude is equal to the ratio of the new intensity divided by the square of the new amplitude. In letter A, we are asked for the new intensity. So manipulating this equation, we now have this. Substituting the given information, we now have 10 squared over 5 squared multiplied by 400. Notice that 10 and 5 were both raised to the same power. So we can divide 10 by 5 first, which is 2, then square it, that gives us 4. 4 times 400 gives us 1,600 watts per square meter. For letter B, we were asked for the amplitude. So manipulating this equation and isolating a sub 2 squared, we have this. And substituting the given values, we have 100 over 400 times 5 squared. 100 over 400 reduces to 1/4, and then we retain 5 squared. We then get the square root of each side, giving us 5 over 2, or simply 2.5 centimeters. Now, notice that in our calculations, the amplitude or the amplitudes were expressed using centimeters, and then the intensities used meters in their unit. But we don't have to convert anymore, since if you look at our equations, the units are actually being canceled out. Okay. So I hope this discussion, guys, gave you an idea or a basic idea about intensity and amplitude. I hope everything's clear. And as always, thank you for learning with me today. See you on the next session of the HPL Files.